The external walls of many older buildings show only too clearly the large amount of pipework used in the drainage system. These complicated arrays of piping are not only untidy, they're expensive and unnecessary. The drainage systems in more modern buildings are much simpler. You can't see the pipework because it's inside. All that does show is the top of the stack. Although less pipework has been used, there is no loss in efficiency, and it certainly costs a lot less to install. Improvements like these are the outcome of research into the hydraulic principles of drainage. Much of this work was carried out at the Building Research Establishment on laboratory rigs such as this, using coloured dyes to show the water flow. The resulting simplified system is an improvement whichever way you look at it. Think for a moment of what a drainage system has to do. First, of course, it must carry away waste materials quickly, quietly and without blockage. At the same time, the foul air in the drain must be prevented from entering the building. A water seal or trap is the answer, which in WCs must also be large enough to receive waste matter. Unfortunately, large pressure fluctuations can cause water seals to be broken. A maximum seal loss of 25 millimeters from a washdown WC is permissible, but a large seal loss can be noisy and allow foul air to enter the building. But what causes these fluctuations and seal losses, and how can they be controlled? One cause is self-siphonage, an effect most often associated with wash basins when the branch pipe runs full. The water flowing down the pipe acts as a piston and siphons water out of the trap. Venting can prevent this by reducing the suction. But tests show that this kind of seal loss can be controlled merely by limiting the length and slope of the waste pipe. Moreover, provided the length and slope are kept within limits, a useful amount of runback occurs, which keeps the trap topped up. Self-siphonage can also be controlled by using a larger waste pipe that doesn't run full. When long branch pipes or bends cannot be avoided, some venting or special resealing traps may be necessary. Basins fitted with S-traps and vertical sections of waste pipe commonly need venting. WC traps are not so liable to self-siphonage because the branch pipe is so large. Neither are branch pipes serving urinals because the water flow is so small. Sinks and baths have large internal surfaces and flat bottoms so that a trickle follows the main discharge, and this helps to keep the trap filled. When branch pipework serves several appliances, seals can also be lost by induced siphonage from appliances not being discharged at the time. This effect increases when more than one appliance discharges at any one time. Tests based on studies of large buildings in use show that up to 4 wash basins can be connected to a straight, unvented 50mm waste pipe without risk of seal loss. But 5 or more basins connected to the same size waste pipe would need a 25mm vent pipe connected to the upstream end. "100mm branch pipes serving WCs seldom run full and rarely need venting. Seal loss due to induced siphonage can also be caused by pressure reductions in the drainage stack. Water flow in the stack causes air to be drawn down, but the water flowing from the branches across the stack restricts this airflow and causes a drop in pressure below the discharge point, causing seal loss from other appliances connected to the stack below the discharging branch. Drainage stacks should therefore be large enough to take the likely maximum number of discharges without restricting airflow. This effect is also more likely to occur when large diameter branch connections, such as those serving WCs, have sharp-edged entries, so they should always be swept in the direction of flow. A vent stack may be needed only if a large number of appliances have to be connected to the drainage stack or if sharp, unswept branch entries are used. This vent stack may be connected by simple cross connections. While self-siphonage and induced siphonage can cause water seals to be drawn out, back pressure, higher than atmospheric pressure, may force foul air through the seals. These back pressures tend to occur above offsets in the stack or close to the bend at the base of the stack when appliances are discharged. Bends restrict the flow of air down the stack and cause the pressures to rise well above atmospheric pressure. Offsets and small radius bends should be avoided, especially at the foot of the stack where it joins the underground drain. Large back pressures can also develop if the drain becomes surcharged with heavy rainfall or floodwater. In these circumstances, the stack must be vented just above the bend or sewer connection. But how can blockage problems be reduced? In practice, good workmanship is essential. Sharp bends and branch fittings should be smoothly curved in the direction of flow, especially in long branch pipes. Badly placed access covers can make clearance almost impossible. To confirm the findings of the work carried out at BRE, the laboratory research was backed up by field tests and observations on many buildings. This research has enabled estimates to be made of the number of appliances which are likely to be discharged at any one time in different types of buildings: offices, schools, domestic buildings, hospitals. For example, in a range of 5 basins, only 2 are ever likely to be discharged at the same time, even in a busy office or public building. Similarly, only 3 WCs from a total of up to 50 are ever likely to be discharged at the same time. This 8-story office building contained a fully vented drainage system, which research suggested should work satisfactorily without venting. Gate valves were incorporated in the system to enable it to operate fully vented, partially vented, or completely unvented. Special intervals over 2 years. Pressures were also monitored continuously for long periods during this time, and it was found that the system worked perfectly well unvented.
By designing drainage systems for the maximum loads to which they're likely to be subjected, and by using good detailing to limit pressure fluctuations and blockages, it's possible to greatly reduce venting and often to eliminate it altogether, even in large buildings. Estimates show that design according to these principles can result in cost savings of up to 30% over traditional fully vented systems. Details are available in Code of Practice 304 and Building Research Digests 80 and 115.